Welcome to the second video for section 2.3. In the first video, we learned how to evaluate functions. And sometimes in evaluating, we have to substitute negative x for x. So the first part of this video is going to help us learn how can we simplify after we substitute in a negative x. So this slide says the following statements are true. Use x equals 8 to show that they are true. So we're going to substitute 8 for x and look at what happens in these equations. So let's start with number 1. We have the absolute value bars here. So I am going to substitute 8. So I keep the negative sign, but I put 8 where the x is. And also on the right side, we're going to put 8. Now with a number in there, we know how to take its absolute value. And absolute value is always positive. So the absolute value of negative 8 is 8. And the absolute value of positive 8 is 8. And this, of course, is a true statement, which means that this original statement with the x's in it is true. So if I ever substitute negative x inside the bars, I can simplify it to be just absolute value of x. Look at number 2. We have parentheses and then negative inside. We're going to put 8 where x is. And on the right side, we're going to put 8 where x is. And I'm going to go ahead and put parentheses around that 8 as well. Here, when it's positive, the parentheses are optional. Okay, so back to the left side. Because the negative is inside, then that means negative 8 times negative 8. And the right side, of course, is 8 times 8. Now negative times negative becomes a positive. So we end up with a true statement. That means when we have negative x inside the parentheses squared, it simplifies to be just positive x squared. Now look at this note here at the bottom of the slide. If the parentheses were not around the negative x, then these would not be equal. Here, if I put in 8 for x, the negative would stay out front. And so you can see that these are not equal. Let's look at a few more. Here we have the exponent of 3. Let's use 8 again. So if I substitute 8 on the left and 8 on the right. Well, on the left side, that actually means you're going to take negative 8 times negative 8 times negative 8. On the right side, the negative just stays out front, and you're going to cube 8. I suppose we could write, erase that cube. Write it out as 8 times 8 times 8. So negative times negative is positive, and then positive times negative is going to make that a negative. And you get 512 when you multiply. On the right, you keep the negative and you multiply the 8s. So both sides turn out the same. So this original statement is true. When you cube a negative x, you get the negative. Okay, look at number 4. Cube root. And this is why I chose 8 as our example number, since it is a perfect cube. But let's substitute and see what happens here. Now, when you take the cube root of a negative number, it just means you get a negative answer. It does not give you an I. The only time you get I is when you take the square root of a negative number. So you're going to have a negative sign, and then you're going to cube root the 8, which is 2. On the right side, you've got the negative out front, it stays, and then you take the cube root of 8 is 2. So these two are the same. So that means when you substitute a negative x inside the cube root, you can simplify it by bringing that negative outside. Okay. So part of why we wanted to look at those statements is because we're going to be substituting in negative x into some functions to see if the function is even or odd. So let's read these definitions. If the graph of a function is symmetric with respect to the y-axis, we say that it is an even function. Now, so graphically, we can just look at the symmetry and see if it has y-axis symmetry. But if we had an equation, we would have to do this part, and it says, for each x in the domain of f, f of x equals f of negative x. And so we'd plug in negative x and see if we get the same result as f of x. So we're going to do some of both. We'll start out with some graphs, and then we'll do some equations. So for the graphs, we check the symmetry. For the equations, we substitute in negative x. And you'll see when we do the examples. Okay, so next it says if the graph is symmetric with respect to the origin, we say it is an odd function. So to help you remember that, think about the O. O in origin, O in odd. Now, for the equations, when we substitute in negative x, if the result is equal to negative f of x, we know it's an odd function. Okay, let's start with the graphs. And I reminded you up here at the top of this slide, it's even if it's symmetric about the y-axis, it's odd if it's symmetric about the origin. So look at number 1 here. Let's go ahead and label. I'm going to change to black. This is x, this is y. It says determine visually whether the function is even, odd, or neither. And it is only going to be one of those. It can't be both even and odd. So what I would do is start by thinking about y-axis symmetry. So let's go ahead and write that down. If we fold this graph over the y-axis, so here's our y, let's pick a point. We'll take this point right here. If I fold it over the y, there's not a point symmetric, okay? Or if you just think about the whole graph, the right side would not lie on top of the left side, so it does not have y-axis symmetry. We're not checking x-axis, by the way, because we want to know if it's even or odd, and the x-axis symmetry has nothing to do with that. So just y-axis and origin. Okay, so remember when we talked about origin, we said if we turn our paper upside down, would the graph look exactly the same as the original? So think about that for this graph. And yes, it would. So that this graph has origin symmetry. Remember, the other way to think about it is pick a point here in the first quadrant. You should have a point through the origin in the third quadrant that's symmetric. And so these two show us that it does have origin symmetry. Now the question was, determine whether the function is even, odd, or neither. And so if we say yes for origin, then we need to go ahead and answer that this is an odd function. So odd is the actual answer here. Okay, number 2, this is x and y. Let's think about y-axis first. So we're looking at the right side. If we fold the right side over the y-axis, would it be on top of the left side? And yes, it would. Or if you need to pick a point, let's say we just pick this point here at the top, it's symmetric to this point about the y. So if y-axis is yes, you don't even need to check origin. You can just go ahead and answer this is an even function. Y-axis symmetry means even. All right, number 3. The axes are already labeled here, so let's do y-axis first. If I fold over the y-axis, is the right side going to lie directly on the left side? And it is not. We see that it has this portion that goes down on the left side. We do not have that on the right side. So no for y-axis. Let's try origin. Think about turning your paper upside down, and would this graph, the graph when you turn it upside down, look the same as the original? And it would not. These ends would be facing down instead of up. So no, it does not have origin. If both of those are no, your answer is neither. It is not even, it is not odd. Go ahead and try number 4. I'm going to give you a couple minutes to think about that on your own. Okay, so for y-axis, if we were to fold the right side over the y-axis, it would not coincide with the left side. It does not have y-axis symmetry. Origin, rotate 180 degrees. Turn that paper upside down, and it would look exactly like the original graph. It does have origin symmetry. Therefore, this function is odd. Now, we didn't have a point in our first quadrant, but you can do the same thing with the second and fourth. So if you have a point here and you go through the origin, if it has a symmetric point in the second and fourth quadrant, yes, it has origin symmetry. So that's how you determine if a graph is even or odd. Next, we're going to look at some functions that are in equation form and determine if they are even or odd. So we don't have the graphs to look at here. So look up at the top of the slide. Definition of even is that f of x equals f of negative x. So the first thing we're going to do on these problems is find f of negative x, compare it to your original. If they are the same, we can say the function is even. So let's go ahead and start with that on number 1. We're going to find f of negative x. So for each x, we substitute negative x. Let's put parentheses around it when you substitute it. So here, and then we bring down our minus 6, substitute in the negative x, keep the exponent, and simplify. Now, this is where those statements that we started with on this video come in. If I have a negative inside and an odd exponent, it results in a negative. So I could go ahead and say this is going to be negative times a positive 5 is going to make the result negative. So I'm going to put that negative out front, and then the 5, and then the x to the 7th. Here, again, I have an odd exponent, so the result of this negative x cubed is going to be negative times the negative in front of the 6 is going to make positive 6x cubed, and drop down your minus 2. Now compare that to your original function, and we can see here on the first term the signs are not the same, nor are they on the second term. This does not equal f of x. Oops. So it does not equal the original function, then it is not even. So I'm going to go ahead and write that just so we understand what we're determining here. And I'm going to kind of put a little line to separate. Then the next thing we need to do is check, well, is it odd then? So look at the odd statement. F of negative x is equal to negative out front of the whole function. Well, we've already computed f of negative x. The result is here. So next we need to say, okay, what if we stick the negative out front of f of x? Now then you would just keep the negative and it would be out front of the whole function. So put the parentheses and then substitute your original function. We're getting from up here. That's f of x goes inside, the negative out front of the whole function. Now to simplify that, you would distribute the negative. So negative 5 and negative is going to make that positive 6. And negative makes that positive 2. So now we're comparing this answer to this answer. We want to see, is negative f of x equal to f of negative x? The negative out front equal to the negative inside. Well, the first two terms are the same, the second two terms are the same, but the last term is not. We've got a negative 2 here, a positive 2 here, so it does not equal f of negative x. So it is not odd. If it's not even and it's not odd, the answer is neither. Okay, so that's how these problems work. We're going to practice several here. This time we're calling it g of x, but it works just the same way. The first step is to find g of negative x. So we're substituting negative x for the first x. Put parentheses around it when you substitute, when you have an exponent. Then you've got your plus, absolute value bars, and then the negative x goes inside. Now, to simplify that, and this is where you need to think about those statements that we went over at the beginning of the video. If you need to go back and look at those, go ahead. Now, we had squared, but it would be the same results for any even exponent. A negative inside with an even exponent will always turn positive. If we wrote it out, it'd be negative, 4 negatives, which would multiply to be positive x to the 4th. I'm going to bring down my plus. And we also had this statement that said absolute value of negative x equals absolute value of x. So when it's absolute value of negative, you can always go ahead and say, okay, that's going to be the same as absolute value of positive x. Now let's compare that to our original, and they are exactly the same. This is equal to g of x. That means the function is even. If substituting negative x results in the original, the answer is even. Okay, number 3. Again, let's start with negative x, f of negative x. So we need a negative x in for this first x here. Then we've got our radical, 1 minus, and then we're putting in negative x squared. Next, we're going to simplify that. Now, since we don't have an exponent, or I guess you could just say the exponent's 1, then negative x is just negative x. Radical, 1 minus. Here, when we square the negative, it becomes positive. Now, I still need this negative that's out front, comes down, but this is going to turn into x squared. Now I compare that to my original. It's the same inside the radical, but that x out front has a different sign, so this does not equal f of x, meaning it is not even. Okay. When it's not even, the next step is you put negative in front of f of x. So it's going to be a negative in front of this whole function. Now, This function is just one term. Since the x is multiplied by the radical, terms are separated by plus or minus. So if there had been a plus sign in between, it would be two terms and we'd have to put it inside parentheses. But because it's just one term, it's a product, then we just stick the negative out in front of that term. And then we're going to write down our f of x. And that cannot simplify any further. We compare that to our answer, f of negative x, and that is equal to that. So we're going to write that equals f of negative x. Therefore, it is odd. If the negative out front results in the same as the negative inside, the answer is odd. Okay, one more example real quick. Number 4, you only have a constant on the right side of your equation here. So if you were to try to find h of negative x, there is no x to substitute in for. This function is constant. It's going to stay 2 no matter what I substitute. No matter what's inside the parentheses, it just stays 2. And therefore, it is equal to the original. So the answer is even. This is equal to h of x. Now let's think about the graph real quick, just to help you kind of see why it works that way. Remember, this is the same thing as the equation y equals 2. H of x could be replaced with y. And if we go to 2 on the y-axis, y equals 2 is just the line, the horizontal line that goes through there. And so if we think about the symmetry of that line, here's our y-axis. It's symmetric about the y. This side of the line would lie directly on top of the left side, so it has y-axis symmetry, which is another way to see that even is the correct answer. Okay, so that brings us to the end of 2.3. Be sure that you work on the homework and let me know if you have any questions.